So in the last video, we explored what a buffer is and we derived this equation called the Henderson-Hasselbalch equation, which we're going to use the pKa and the log of the concentration of the base over the concentration of the acid to solve for the pH of the buffer. So now let's go ahead and take a look at an example problem. So let's say we make a buffer solution by combining 50 milliliters of 0.250 molar acetic acid and 75 milliliters of 0.18 molar sodium acetate, and then we're looking for the pH of this solution. So we're going to keep the Henderson-Hasselbalch equation in mind. So let's go ahead and write down our givens. So we have 50 milliliters, and that is of 0.250 molar HC2H3O2. We also have 75 milliliters of 0.180 molar sodium acetate, so NaC2H3O2. And because I don't feel like writing, let's go ahead and abbreviate this as HA. We're going to define this to be HA, and this will be NaA. So the A here represents the acetate ion, the anion. And then we know from either a table or we give it to us a problem that the Ka for sodium acetate is equal to for acetic acid is equal to 1.7 times 10 to the negative 5, which makes sense because we're dealing with a weak acid here. So if we look at the Henderson-Hasselbalch equation, so we scroll back up, if we look at the Henderson-Hasselbalch equation, we know that we can use the initial concentrations of the acid and the base because the Ka is so small. So for example, the Ka is so small here that it actually doesn't make considerable difference when dealing with sig figs. And I know I neglected sig figs here, but that's just for the sake of writing. So you might say, well, we have 0.25 molars of the acid, so we'll plug that in down here. We have 0.18 molar of the base because this associates into Na plus and T2H3O2 minus. But you'd actually be wrong in this instance. And why would you be wrong? Well, what we're actually doing is we've got a beaker. It's a very short beaker, but we've got a beaker, and we're actually adding in. We'll say that's the acetic acid, and then we're adding in the sodium acetate. So in the beaker, we're going to have a solution that is a new volume. And what's that volume going to be? It's going to be 125 milliliters because we have 50 milliliters of this, 75 milliliters of this. So we actually can't just use these initial concentrations. So what we could do is we could go and say, well, we can use our equation M1V1 equals M2V2, go in and find new concentrations under the new volume. And that is absolutely fine. You can actually do that. But what I'm going to do is I'm actually going to put these into moles. And why can we put them into moles? Well, if we have moles over liters, and then this will be times the reciprocal of that whenever we're dividing, so that will be times liters over moles. Well, they're in the same volume, so we can actually just cross out liters and put moles of the base over moles of the acid here. And so let's go ahead and do that, and we'll see that converting to moles is actually going to help us in a second part of the problem where we're going to add a strong acid to the buffer. Let's go ahead and do that. So we know for here we have 50, and then we can't use liters, or milliliters, so we need to convert that. So it'd be 50 times 10 to the negative 3 liters times 0.250 molar. And what does that give us? Well, that gives us 0.0125 moles of sodium acetate, which I should have written as HA because I defined it up there, but that's okay. I'm going to do the same thing down here. So we have 75 times 10 to the negative 3. And if you're not familiar with using this kind of conversion, it's almost a shorthand. So we know that milli is times 10 to the negative 3. So we just slap that on there. it ends up working in the end 0.180 molar, and that gives us 0.0135 moles of Na, and then we'll just repeat that as A. So what's actually going on in our reaction here? I always like to write down the reaction. So we know we have sodium acetate, so we have HA plus H2O, which we know is a liquid because we're in aqueous solution, and that's in equilibrium with the hydronium ion, plus, which we could abbreviate as H plus, and the anion, which is the conjugate base, so A minus. We also have NaA, so let's color here. So we have NaA, which is sodium acetate, and we know that sodium salts dissociate completely, so we're going to say that that goes to full for Na plus plus A minus. Okay, so now we know everything because we have our new moles. So we have 0.0135 moles. So because it's a 1-to-1-to-1 ratio, so we just have a bunch of ones out here if that's more visually appeasing to you. And so that means we have 0.0135 moles. This is moles of this. So what we can do is we could take this and put it over here. So we have 0.0135 moles, and then of course we have 0.0125 moles of our acid, our sodium acetate. So now we can go ahead and plug everything into the Henderson-Hasselbalch equation. So we know that pH is equal to the pKa plus the log, and just for visuals, we're going to say the base over the acid. Okay, so we know that pH is equal to the negative log of the Ka, which was 1.7 times 10 to the 5th, and that's plus the log of the moles of the base, which is 0.0135, over 0.0125. And so what does that give us? So the negative log, or the pKa, ends up being 4.7696, and we're just going to add some significant figures onto that, and then 0.03342. So we know that pH equals 4.80. So that is our pH that we were able to solve for, 4.80. So now we're going to add some more space here for the second part of our problem. Okay, so we know that the pH of our buffer solution is 4.80 with those specific volumes and concentrations of acid and its conjugate base salt. So now what happens to the pH if we add 3.75 milliliters of 0.300 molar, and we're going to just slide over here so we have a little bit of space, 0.5 molar HClO4. And that's perchloric acid, so we know that perchloric acid is one of the strong acids we memorize. We can also say that it doesn't have a Ka value on a Ka table. So let's do the same thing here. So we have, let's zoom out a little bit. So now we have 3.75 milliliters, and that's of 0.300 molar HClO4. Well, we can do the same thing here. We can solve for the moles. So we can say that we have 3.75 times 10 to the negative 3 liters times 0.300 molar, and that gives us a value of 0.00125 moles, and that's of HClO4. Okay, well now let's look at what's actually reacting here. So we know that because we have an acid, the acid is going to react with the base part of the buffer. So of HClO4, and that's going to react with the sodium acetate, and then that, because we're adding a strong, and of course this is a sodium salt, that's going to drive to completion and give us Hc2H3O2, and of course NaClO4. When we break this down, we could break this into its net ionic reaction, so we end up just getting that we have a proton, which is H plus C2H3O2 minus, and that's just going to yield HC2H3O2. And so now we know that because we have a one-way arrow, we can't use an ice table. We have to actually look at a limiting reactant problem. So this is going to be a limiting reactant. So let's go through and do this, and we're going to do this kind of a shorthanded way. It's a lot easier, but you can actually do it where you set up all the, all the parentheses and go through. But it's just a lot easier to think of it this way, especially since everything's a 1-to-1-to-1. So we know that we have, let's get a new color here. So we know that we have 0.001125 moles of that. And from this, we found this in the first part of the problem. If you want to see that, we found this in the first part of the problem. So we have 0.135 moles. And this is all in moles, by the way. Just throw that over here. And then we know that from the initial part of our problem as well, we have 0.0125 moles. And so we can see that up here, we have 0.0125 moles of the acid. So what's our limiting reactant in this case? Well, our limiting reactant is whatever we have less of, because it's a 1-to-1-to-1 ratio. So we know that we can go ahead and we can subtract 0.001125, and then we can subtract 0.001125 moles from this, and of course, because it's on the other side of the reaction, we are making 0.001125 moles. And so whenever we subtract and add here, we end up getting 0, because this just cancels out. We get 0.014625, and we're just adding extra digits. We'll do our significant figures and round later, and then we end up with 0.013625. And so after we have our limiting reactant, this is what we have left. So we have excess conjugate base left, and we have an acid that we have made more of. So now if we go into our equation, and I just want to make sure I have enough space here, so we're going to add just a little bit more space. So if we go back to our equation, we know that pH of a buffer, because we still have a buffer here, because we've not reached the buffer capacity, is equal to the pKa plus the log of the acid the base over the acid. And so we know that pH, and we solved for the pKa earlier in the problem, which is 4.7696 plus the log, and we have new molar concentrations here. We have 0.014625 over 0.013625. And so when we get this, we get pH. pH is equal to 4.7696 plus 0.0307. And so in the end, what is our pH? Well, our pH stays the same. We'll just write this over here. The pH is equal to 4.80. So we see that the buffer solution, with the addition of just a small amount of hydrochloric acid, actually changed the pH by nothing. It actually stayed the same. So we do know that we are dealing with a buffer solution, especially here, because we are able to remain at a stable pH. And so that's all I have for you for this time. And next time we will maybe go and do a little bit more buffer type problems using strong species, so partial neutralizations, and then we'll get into acid base titrations. So thanks.